Okay, folks, I did not get to finish these last couple of slides with you on Thursday, and obviously I'm out today, so I want to go ahead and wrap up these notes here. So on these last two slides, this is where we're going to talk specifically about horizontal launch. So all the other three types of launches we talked about on the first slide of these notes, the angled ones, that will come at a later time. So right now what we're going to do is just to focus on the horizontal type launches. This slide is very important because it gives you some straight up facts about these horizontal launches. So for example, remember if it's a horizontal launch, the path the projectile takes looks like half a parabola that opens downward. Now I'm going to redraw that same picture I did on the very first slide of these notes. Remember with the horizontal launch, the launcher is sitting on something, so there is a vertical displacement. So here's my launcher, and bam, it gets fired, so here it comes the object. Notice that there is no upward path to this projectile. We only have the downward path, so that's why we call it a half a parabola. Now, that takes me to this piece right here. This means that your initial velocity in the y direction must be 0. Think about it. If this is being shot horizontally, is there any motion upward in the vertical direction? There is not. So that is why the velocity in the y direction, the initial velocity in the y direction, will always be 0 for a horizontal launch. The only initial velocity we're going to have is in the x direction, whatever velocity this gets shot out at. Your next bullet, the total vertical displacement will be negative always, you guys, for a horizontal launch. Let me prove that to you. Let's say this launcher is 2 meters high. So if you think about your displacement equation, displacement vertically is final minus initial. And the final is going to be when the object hits the ground. So the final position is 0 minus your initial position, and it starts 2 meters up. So 0 minus 2 is negative 2. So there it is. There's the negative vertical displacement. And that will always be true for any horizontal launch. This last bullet is just reiterating what the first bullet says. The projectile never goes up. It only goes down. So what we're going to do right now is we are going to go ahead and do the one example problem I give you for a horizontal launch. I only gave you one because they are longer. So it says, a toy car rolls horizontally off of a table that is 1.45 meters above the ground. If the car leaves the table with a velocity of 2.45 meters per second, how long does it take for the car to hit the ground? And how far away from the table does the car land? So right away, I want you to notice something that I underline. I straight up tell you horizontally, so you know this is a horizontal launch. So look for those buzzwords. So I'm going to go down here, and this is where I'm going to do my work for this problem here. And I have the equations pasted here for you, so it's easy to see. Whenever you're doing a projectile motion problem, you need to have a T-chart of knowns. This will always be your first step. You're going to have your knowns in the x direction and your knowns in the y direction. So right away, what I always do is I get my acceleration values down. Remember, acceleration in the x direction is always 0. We talked about that earlier in the notes. There is no acceleration horizontally. There is nothing pushing or pulling this object horizontally. There is no air resistance. And you know, vertically speaking, our magic number, acceleration in the vertical direction, is always that negative 10 meters per second squared. Now what I'm going to do is one of the first numbers we underline was this 1.45 meters. They tell you how high up this toy car starts. So how high up, that's a vertical measurement. So you know that your y initial is 1.45 meters. That's its initial position. Therefore, this car does end up hitting the ground, so we can say that y of f, our final position, is 0 meters. the initial velocity in the y direction. So our VIY, initial velocity in the y direction, remember it's a horizontal launch. So with the horizontal launch, it gets shot straight out and down like the picture we drew on the last slide. So there is no movement of the object in the upward direction since it's shot horizontally. So remember, your VIY is always 0 meters per second for a horizontal launch. Now, the next number that we are given is the car leaves the table with a velocity of 2.45 meters per second. So that is your initial velocity in the x direction, 2.45 meters per second. Now here's the thing, you guys. There is no launch angle here. It's 0 degrees, so we don't need to do components. But remember, technically, we have our components. Here they are. Here's the VIX, here's the VIY. And if you don't believe me, you can go ahead and use your component equations and plug your values in. You can do 2.45 cosine of 180 and you'll get this. And you can do 2.45 sine of 180 and you'll get this. So the components we were able to get easily because of it being a horizontal launch, meaning the launch itself was one-dimensional since the angle was 0 degrees. Okay, let's see. We are asked for how long does it take for the car to hit the ground. That's the time of flight. How long does it take for it to fly through air and hit the ground? I always write T right on the middle of my T chart, because remember, time can flow freely back and forth from one side to the other. Time does not have a subscript to it. And then in part B, we are asked how far away from the table does the car land? That's a horizontal position. How far away once it hits the ground does it land when it hits the ground from the table where it started at? So that's an x of f. We need to find our final position horizontally. And then there's one last thing we can plug in here. X of I is usually just always 0 for us. So look at all that. A bunch of knowns in the x and in the y direction. So I would always try to solve for time first. It's just kind of our rule of thumb. So if we look at our equations here, a lot of you are going to say, oh, let's go to this one because it's short and it's easy. But if you take a look, you don't know time and you don't know x of f. So you have two unknowns, so that equation will not work. So it's got to be something on this side. If you go to this one, there's time, but we don't know the final velocity. So once again, two unknowns won't work. This equation has no time in it, so therefore it's got to be this one, the middle one. So here we go. Y final equals Y initial plus VIY times time plus 1/2 AT squared. Now, please notice, you guys, that I am using subscripts on everything. Okay, so my initial velocity, I have VIY. My A, I have the subscript of Y, because we are talking just the Y direction here, the vertical direction. Now, just like kinematics, get rid of your 0 stuff. So Y final is 0, and your VIY is 0, and 0 times anything is 0, so this whole chunk is gone. So look what we have left. So we are trying to find time, so I'm going to get rid of this single guy by moving him over to the other side. So negative y of I is equal to 1/2 AYT squared. And now we just do our algebra. Physics is done. So I'm going to get rid of my fraction by multiplying by the reciprocal. So I'm going to multiply by 2. So 2 times negative y of I equals AYT squared. And I'm going to get rid of A, so by dividing them over, equal to T squared. And now lastly, to get T by itself, we have to square root everything. So 2 times my negative y of I, so it's going to be that negative 1.45 divided by my acceleration in the y direction, which is negative 10. And if you do that math, folks, and square root it, you're going to get t is equal to 0.53 seconds. And that is how long it takes the car to hit the ground. Now, remember our other unknown, part B, was finding his final position horizontally. So, go back to your equations here. We want x of f, and really, you guys, this is the only equation we have that has x of f in it. So I'm going to go ahead and write that down. And get rid of my 0 stuff, so x of I is 0. And you're just left with x of f is equal to v ix times t, keeping my subscripts. And we are going to go ahead and plug and chug. So my initial velocity in the x direction is that 2.45. And the time is what we just got. So x of f is going to equal 1.29 meters, and that's how far away this car lands on the ground from the table. So this is the process you will go through to get through any horizontal launch problems, always starting with your T-chart. That's the hardest part, is getting the knowns. Once you have the knowns down, then it's a matter of picking the right equation again. Okay, we are now going to move on to our problem set for you to do a little bit of independent practice.